Change defines motion. In this video, we'll look at another change, acceleration, and develop the 5 standard kinematics equations. Well, we set out in this unit to define motion, so we had to introduce what we would observe to gauge this motion. It started with position, and our object could be in any number of these. Moving between these locations had us introduce the concept of displacement, a change in position. And of course, it takes time to observe this change. So our story grew when we considered another concept, velocity, the rate of change of position with respect to time. But a picture's worth 1,000 words, so we introduced graphs to help us describe this motion. We can relate position with time, or velocity with time, and these graphs help us see at a glance another descriptor. Is the motion uniform, in which case our position time curve doesn't look curved at all? Well, it actually is a curve, it's just the curvature is 0. And our velocity time graph is a horizontal line, the 0 slope indicating no change to the velocity. Or is the motion non-uniform? Our position time curve now is curved, and the changing slope gives an indication of the changing velocity. And then our velocity time curve is now a diagonal line. Perhaps its slope has a story to tell. Well, our non-uniform motion suggests we can observe different velocities at different times, and if that's the case, we should probably introduce a delta for this variable. And that leads to the introduction of a new character as the story unfolds. Enter acceleration. Just like we did with velocity, it just comes down to establishing a definition, a conventional descriptor that we all agree to use to describe this rate of change of velocity. Note that the relationship between acceleration and velocity is identical to the relationship between velocity and position. And the interesting thing about similar forms in mathematics is we use related processes to perform analyses. It's kind of like taking the bus to the mall, or taking it to school. The process is the same, the results are in the details. And this is true when we look at our different motion graphs. We're familiar with position time and velocity time, and we'll extend our ideas to acceleration time. We'll limit our discussion there as we'll only consider uniform acceleration. Non-uniform acceleration is for jerks anyways. So for uniform motion, position time and velocity time look like this, and here's how they look for non-uniform motion. Now the slope of our position time graph is the value of the velocity at the point where the slope was taken, while the area under a velocity time curve over a period of time tells us how much the position is changed over that interval, the displacement. Using a parallel process from velocity to acceleration time graphs, the slope of the velocity time curve provides the value of the acceleration, which of course is 0 for a uniform motion, and for this example of non-uniform motion is a negative value. While the area under the acceleration time curve over a time interval gives the change in velocity over the same period on the velocity graph. Of course, for uniform motion, the acceleration lies on the time axis, so the area is 0, and the area for the negative acceleration is under the time axis, indicating a negative change in velocity. But this idea of negative acceleration is not quite as intuitive as it might seem at first. Notice from the graph that the acceleration is negative, but looking at the velocity time curve, when the velocity has a positive value, it slows over time. Its scalar corollary, speed, is getting closer to 0. But when the velocity is negative, or moving in the opposite direction, the speed increases. So it appears that the same acceleration can speed something up or slow it down. Now luckily, like in all of physics, there's a pattern that we'll see if we look closer. And for that, we'll go back to that physics cart from the last video where we pushed it with a fan. Now we'll review the motion we've already seen, but we'll consider 3 other options. These are listed on the screen. If you don't have this worksheet and want to get one, you can follow the link in the video description below to download and print your own copy. Now this video will work best if you pause it each time you see the cart's motion and predict what you expect all the motion graphs to look like when we run the demo. So there's the first one, and pause. Now for each scenario, we'll start with a sketch to set up our analysis and move to the right. So let's start with the direction. Now our positive direction is an arbitrary choice, but for this analysis, we'll consider motion to the right as positive motion. This sets up direction for all the vectors in our analysis, starting with the force, which is also in our positive direction. So let's look at the position time graph. No surprises, the slope starts at 0 and increases positively as it speeds up. And the velocity time graph is as we would expect from the last video, a uniform positive slope. And since our velocity slope gives acceleration, we have a uniform positive value. So to sum up scenario 1, the cart speeds up while the velocity and acceleration are both positive. And this brings us to scenario number 2, where the motion described on the worksheet is shown here. Well, the force in this scenario is in our negative direction, as is the motion. Like scenario 1, the initial velocity is 0, but in this case, the slope of the position time curve increases in the negative direction, as does the value of the velocity time curve. And since the slope of this graph is uniformly negative, so is the acceleration. So it speeds up in the negative direction due to negative acceleration. Now let's consider scenario number 3. Unlike the first 2 scenarios, the cart is initially moving, and the fan is blowing to oppose this motion. So here, with the force of the fan opposing the cart's initial velocity, the fan slowed the cart down as we see a position time curve with a positive slope that decreases. Now this gives rise to a positive but falling velocity as it slows, and the negative slope on the velocity-time relation indicates a negative acceleration. So to sum up scenario number 3, the cart slows down with positive velocity but negative acceleration. And that brings us to our final scenario. Again, the cart is initially moving, but to the left this time, while the fan opposes its motion. Now the initial velocity here is in our negative direction, but the force of the fan is directed positively. This yields a position time curve with an initial negative slope that reduces as the cart slows, and the velocity time graph, initially at a relatively high negative value, has a positive slope indicating a positive acceleration. So wrapping up this scenario, the cart slows down when the velocity is negative and the acceleration is positive. Now notice that in these last two scenarios, the cart slows whenever the velocity and acceleration oppose each other, while it speeds up when the sign of the velocity and the acceleration are in agreement. There's also a link between the force of the fan and the acceleration, but we'll explore this in a later video. Now ultimately the aim of this video is to derive the 5 standard kinematics equations. We need 5 since there are 5 variables associated with motion. We started with displacement and time and derived velocity, but if velocity changes there will be both initial and final values. And the final variable we need to describe any motion is acceleration. Now if you think back to grade 10 math, when there are 5 variables we need at least 5 equations or no unique solution exists. Now the first standard equation is really just a rearrangement of the acceleration definition. If a is delta v over delta t, and delta v is just the difference between the final and initial velocities, we can write this equation like this. The rest will take a little more work to develop. Well, we've got a relationship between velocity, displacement, and time, and a similar association between acceleration, velocity, and time. So it looks like the connection between acceleration and displacement is like acceleration knows a guy who knows a guy. Let's see if we can't reduce the degrees of separation. For that, let's tell a story within a story. Well, let's say that we know a guy who knows a guy, and that guy is as fast as it gets. Now our guy, Slarta Bartfast, wants to challenge the track star to a 100-meter race, but our guy's not stupid. He hangs around with physics students after all, and he figures he stands a chance if he gets a running start. But before he dares to make the boast, he comes to his physics friends to see if they recommend he issues the challenge. Of course, we need some information to figure this out. Now Slarta Bartfast feels he has enough room before the start line to be moving at 5.2 meters per second, and he'll reach his top speed that he claims is 9.8 meters per second about 3 seconds after passing the starting block. After that, he finishes the race running full out. Now, the world record of 9.53 seconds is a bit of a stretch, but on a training day, our star's slowest 100-meter race clocks in at 10.15 seconds. So the question is, should Slarta Bartfast issue the challenge? Okay, let's look at our information. In our 100-meter race, we accelerate for 3 seconds and move uniformly to the finish. So we have the info, but let's consider our tools. We have our velocity equation. That'll work for the uniform motion, and acceleration combines velocity and time, but we haven't connected acceleration and displacement yet. Well, what about graphs? The uniform motion is easy to work with on a position time graph, but the beginning of the race has increasing velocity. So that's a curve. It's tough to draw and tough to read. Maybe not the best tool for this. Now the velocity time curve looks promising. The area under that plot will give us distance, and the shapes are reasonable for both the uniform and non-uniform parts of the race. Why don't we start with that? Well, the uniform motion is easy. It's just a rectangle. It doesn't get much simpler than that for areas. The start of the race is a bit of a challenge though. It's a trapezoid. But isn't our trapezoid just a rectangle and triangle added together? Now that's an angle to pursue. Okay, so we set up our area equations like this. The rectangle is the height times base, so that's v1 delta t. So far, so good. Now for the triangle. Well, this is half of the height times the base, and our height is delta v, and the base is delta t. Now if we take our acceleration equation and rearrange it to isolate delta v, we get a times delta t. Substituting this, the expression to find the triangle area is 1/2 a delta t squared. So our areas added together to find our displacement involve acceleration, the starting velocity, and the time. Now we're getting somewhere. In fact, this is one of our big 5 kinematics equations. Of course, that's not the only way to approach this situation. With a little change in strategy, we can reduce that trapezoid to a rectangle, and then the calculation is pretty straightforward. Remember from our graphing video, we saw that the average velocity for a time interval has the same value as the midpoint of the interval. If we use the average velocity as the height of a rectangle and multiply this by our time interval, we get the displacement. And to find the average velocity, we just add the two end velocities and divide by 2. So now our area looks like this. Well, we don't really connect our acceleration and displacement with this, but we did find another of the big 5. But what about Slarta Bartfast? Well, if we can determine how far he runs in the first 3 seconds, and he runs the rest of the race at his top speed, we're pretty sure we can determine how long he'll take. Let's see if we can use that first of the big five we found. We've got our v1 in time, and acceleration is pretty easy, or at least getting the number is straightforward. But let's pay attention to the units. We've got meters per second divided by seconds for meters per second, or meters divided by seconds squared. So the conventional unit for acceleration is meters per second squared. Plugging these in, we find that Slaughter-Bartfast travels 22.5 meters in the first 3 seconds. So that leaves 77.5 meters at 9.8 meters per second. Rearranging our velocity expression and subbing in these values, it takes him 7.91 seconds to finish the race. Now add that to the 3 seconds to start, and it looks like Slaughter-Bartfast's time comes in at 10.91 seconds. Not quite enough to take the ribbon, but a valiant effort. In fact, one of his physics friends claims Slaughter-Bartfast never stood a chance. I wonder what her reasoning was. Well, so far we have 3 of the big 5 kinematics equations. Now it's possible to derive the other 2, either algebraically or like we did with motion graphs, but in the interest of time, we'll just list them here. After all, our focus in this course is using these equations well rather than deriving them. And a key component of using them well is the consistent use of positive and negative directions. It's those relative directions for displacement, velocity, and acceleration that must describe whether the object is speeding up or slowing down.